Physics paradoxes challenge everything we think we know about reality and the universe. These mind-bending contradictions have puzzled the greatest scientific minds for centuries and continue to reveal how strange our reality truly is. Over the next 3 hours, we'll explore fundamental contradictions in physics that shake the foundations of what we consider possible. Paradoxes where light behaves impossibly, where time bends and warps, where objects exist in multiple states simultaneously, and where the very fabric of reality seems to break down when examined closely. The quantum realm, where particles smaller than atoms behave in ways that defy common sense, will challenge your intuition. We'll discover how particles can be in two places at once, how they can communicate instantly across vast distances, and how the act of measuring something can fundamentally change what is being measured. These aren't just theoretical curiosities. They're fundamental contradictions that have led to technologies powering our modern world, from computers to medical imaging. Let's begin with a simple question. What is reality? We think we understand it. We see objects, we touch surfaces, we experience time flowing from past to future. But when physicists began probing deeper, they found something unsettling. Reality doesn't work the way we think it does. At its most fundamental level, the universe operates according to rules that seem contradictory and impossible from our everyday perspective. Take light, for example. Is it a wave or a particle? For centuries, scientists debated this question, with compelling evidence for both sides. Waves spread out, diffract around corners, and can interfere with each other, all behaviors that light demonstrates. But particles are discrete objects that travel in straight lines and collide with things, behaviors that light also shows. This wave-particle duality stumped physicists until they realized something profound. Light is both a wave and a particle simultaneously, behaving differently depending on how we observe it. This dual nature extends beyond light to all matter in the universe. Electrons, protons, atoms, and even entire molecules exhibit this wave-particle duality. The famous double-slit experiment demonstrates this perfectly. When individual particles are fired one by one through two slits, they somehow interfere with themselves, as if they were waves passing through both slits simultaneously. It's as if each particle travels through both slits at once, interfering with versions of itself from parallel realities. Even more bewildering is quantum entanglement, what Einstein called spooky action at a distance. Two particles can become entangled, creating a situation where measuring one instantly determines the state of the other, even if they're separated by billions of light years. This seems to violate a fundamental principle of physics, that nothing, not even information, can travel faster than light. Yet experiments have repeatedly confirmed that entanglement is real, suggesting connections in our universe that transcend space and time as we understand them. The paradoxes deepen when we consider time itself. Einstein's theories of relativity showed that time isn't absolute, but flows differently, depending on gravity and motion. The famous twin paradox demonstrates how time dilation works. If one twin travels on a high-speed spaceship while the other remains on Earth, the traveling twin would return younger than the stay-at-home twin. Both twins would experience time passing normally from their perspective, yet they would disagree about how much time had actually passed. This isn't science fiction. It's been confirmed by precise atomic clocks on planes and satellites. Consider also the information paradox of black holes. According to quantum mechanics, information cannot be destroyed, yet black holes appear to destroy everything that falls into them. This contradiction between quantum mechanics and general relativity remains unresolved, suggesting our understanding of at least one of these fundamental theories is incomplete. These reality-breaking paradoxes aren't just academic curiosities. They touch on profound questions about the nature of existence itself. If particles can exist in multiple states simultaneously until observed, what role does consciousness play in shaping reality? If time flows differently in different reference frames, is there an objective now that everyone can agree on? If information can't be destroyed, what happens to the information that makes up your thoughts and memories? As we journey deeper into these physics paradoxes, you'll find your understanding of reality transforming. The solid world around you will begin to seem more like a probability cloud. Time will no longer feel like a river flowing in one direction, and space itself will start to seem less like an empty container and more like a dynamic fabric intertwined with time. Prepare to have your perception of reality challenged as we explore the universe's greatest contradictions, from the quantum realm to the cosmic scale, revealing a reality far stranger and more fascinating than we could have imagined. The most puzzling aspect of quantum physics is that reality seems to exist in a state of probability until we measure it. This principle, called quantum superposition, suggests that particles don't have definite properties until observed. Instead, they exist in multiple states simultaneously, a concept that challenges our fundamental understanding of reality. Quantum superposition isn't just a theoretical curiosity. It has profound implications for how we understand the universe and our place within it. Consider Schrödinger's famous thought experiment: a cat placed in a sealed box with a radioactive atom, a Geiger counter, and a poison vial. If the atom decays, the counter detects it, releases the poison, and kills the cat. Until we open the box, quantum mechanics suggests the atom exists in a superposition of decayed and not decayed states, which means the cat would be both alive and dead simultaneously. This paradox illustrates how quantum effects, when extended to the macroscopic world, create seemingly impossible contradictions. The Copenhagen interpretation, formulated by Niels Bohr and Werner Heisenberg, attempts to resolve this by suggesting that quantum superposition collapses into a definite state only when observed. This raises profound questions about measurement and consciousness. Does observation require a conscious observer, or does any physical interaction constitute a measurement? Does the universe exist in a definite state when no one is looking? Alternatives like the many worlds interpretation suggest that reality doesn't collapse into one state. Instead, it branches into parallel universes containing all possible outcomes. In this view, when measuring a quantum particle, we're simply discovering which branch of reality we're in. This means there are countless versions of you reading slightly different versions of this text in parallel universes, a mind-bending implication from what started as a mathematical solution to quantum puzzles. These interpretations aren't merely philosophical. They affect how we approach fundamental physics. The quantum Zeno effect demonstrates that continuous observation can actually prevent quantum systems from evolving. Researchers have shown that repeatedly measuring an unstable particle can prevent it from decaying, as though watching a pot actually prevents it from boiling. A complete reversal of our intuition. Quantum superposition also enables quantum computing, which harnesses this ability of particles to exist in multiple states simultaneously. While classical computers process bits that are either 0 or 1, quantum computers use qubits that can be both 0 and 1 at the same time, allowing them to perform certain calculations exponentially faster than traditional computers. This technology could revolutionize fields from cryptography to drug development, all based on a paradox that challenges our basic understanding of reality. Consider the double-slit experiment, first performed with light by Thomas Young in 1801. When light passes through two parallel slits, it creates an interference pattern on the screen behind, evidence that light behaves as a wave, interfering with itself. But Einstein showed that light also behaves as particles called photons. When individual photons are fired one at a time through the slits, they still create an interference pattern over time, as if each photon passes through both slits simultaneously and interferes with itself. The paradox deepens when detectors are placed at the slits to observe which one each photon passes through. Remarkably, the interference pattern disappears, and the photons behave like particles, passing through just one slit or the other. Somehow, the act of measurement forces the photon to choose one path, collapsing the superposition. Even more bizarre if the information about which path the photon took is erased after it passes through the slits, but before it hits the screen. The interference pattern reappears, as if the photon's past behavior changes based on our future decision to erase the information. This quantum erasure experiment suggests that causality, our fundamental notion that causes precede effects, may not be as straightforward as we thought. It appears that future events can influence past behaviors at the quantum level, challenging our linear understanding of time. The implications extend beyond the laboratory. If reality exists as probabilities until measured, what does this mean for free will and consciousness? Some physicists speculate that consciousness itself might be a quantum phenomenon, potentially explaining subjective experience through quantum effects in the brain. Others suggest that quantum uncertainty provides the physical basis for free will, creating space for choice in an otherwise deterministic universe. Quantum superposition also underlies quantum tunneling, the ability of particles to pass through energy barriers that should be impassable according to classical physics. This phenomenon enables nuclear fusion in stars, certain types of radioactive decay, and even the functioning of scanning tunneling microscopes used to image individual atoms. Our electronics depend on quantum tunneling in semiconductor devices, meaning the paradoxes of quantum physics aren't just theoretical curiosities. They enable the technology of modern life. As we contemplate these paradoxes, we're left with profound questions. If particles don't have definite properties until observed, is reality created through observation? Is the universe fundamentally probabilistic rather than deterministic? How can we reconcile quantum weirdness with our everyday experience of a seemingly concrete world? These questions remain open, reminding us that at its deepest level, reality may be far stranger than our evolved intuitions can comprehend. Quantum entanglement represents one of the most profound paradoxes in physics, what Einstein famously called spooky action at a distance. When two particles become entangled, their properties become correlated in ways that seem to defy our understanding of space and time. Measure one particle, and you instantly know the state of its entangled partner, even if they're separated by billions of light years. This phenomenon challenges our fundamental intuition about locality, the principle that objects are only directly influenced by their immediate surroundings. In classical physics, if I want to affect something across the room, I need to send a signal that travels through the intervening space, taking time to arrive. But entangled particles seem to communicate instantaneously, regardless of distance. The EPR paradox, named after Einstein, Podolsky, and Rosen, who first described it in 1935, highlights this contradiction. Einstein believed that quantum mechanics must be incomplete because it allowed for these seemingly impossible correlations. He proposed that entangled particles must contain hidden variables, predetermined instructions that explained their correlated behavior without requiring faster-than-light communication. For decades, this remained a philosophical debate until physicist John Bell devised a mathematical framework to test it experimentally. Bell's inequality provided a way to distinguish between Einstein's hidden variables and quantum mechanics' prediction of genuine entanglement. The results were unequivocal. Experiments repeatedly violated Bell's inequality, confirming that entanglement is real. The universe really does permit these spooky connections that appear to transcend space and time. Consider a practical example. Two entangled electrons with a property called spin. Quantum mechanics tells us that, until measured, each electron exists in a superposition of spin up and spin down. When we measure one electron and find its spin up, its entangled partner instantaneously becomes spin down, no matter the distance between them. This correlation happens faster than light could travel between them. Yet no useful information can be transmitted this way, a curious limitation that prevents entanglement from violating Einstein's cosmic speed limit. The paradox deepens with experiments demonstrating entanglement swapping. Here, two particles that have never interacted can become entangled through their connections to other particles. Remarkably, this can happen even after the original particles have been measured, a phenomenon called delayed choice entanglement swapping that suggests entanglement can work backward in time, further challenging our understanding of causality. Preparing and narrating this theory took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the theory. Quantum entanglement isn't merely a laboratory curiosity. It's being harnessed for quantum cryptography, communication systems theoretically impossible to hack because any eavesdropping attempt would disrupt the entangled states, alerting the communicators to the intrusion. Quantum teleportation, the transfer of quantum states between particles, also relies on entanglement, allowing for the perfect transfer of quantum information between distant locations. The implications extend beyond practical applications to our fundamental understanding of reality. If entangled particles maintain their connection regardless of distance, does this suggest a deeper level of reality where everything is fundamentally interconnected? Some physicists propose that space-time itself might emerge from underlying quantum entanglement, that the fabric of reality, as we experience it, arises from a network of quantum correlations. This connects to the holographic principle, which suggests our three-dimensional reality might be encoded on a two-dimensional boundary, like a hologram. Theoretical physicist Juan Maldacena developed the ADS-CFT correspondence, demonstrating how quantum entanglement in one theoretical model corresponds to wormholes in another, suggesting entanglement and space-time geometry might be two perspectives on the same phenomenon. The paradox of quantum entanglement forces us to reconsider our most basic assumptions about reality. It suggests that objects aren't as separate as they appear, that distance might be an emergent property rather than a fundamental one, and that the universe maintains connections between particles that transcend our conventional understanding of space and time. Even more mind-bending is the concept of monogamy of entanglement. Particles can't be maximally entangled with more than one other particle simultaneously. This limitation creates interesting constraints on quantum systems and has implications for quantum computing, where managing entanglement is crucial for maintaining computational advantage. Recent experiments have pushed the boundaries further, demonstrating entanglement between thousands of atoms and even between objects large enough to be visible to the naked eye. As these quantum effects manifest at increasingly macroscopic scales, the line between the quantum and classical worlds continues to blur, challenging us to reconcile these paradoxes with our everyday experience. As we contemplate quantum entanglement, we're left with profound questions. If particles can maintain instantaneous connections across vast distances, what does this tell us about the nature of space itself? Could the universe be fundamentally non-local at its deepest level? And if quantum correlations can transcend time in certain experiments, what implications does this have for our understanding of causality and free will? The paradox of entanglement continues to suggest that reality is far more interconnected and mysterious than our classical intuitions can grasp. Time dilation stands as one of physics' most counterintuitive yet thoroughly proven paradoxes. According to Einstein's theory of relativity, time doesn't flow at the same rate for everyone. It depends on your speed and the gravitational field you're in. Two perfectly accurate clocks will measure different amounts of elapsed time if one moves quickly or experiences stronger gravity than the other. This isn't mere theory. Atomic clocks on airplanes run slightly faster than identical clocks on Earth. GPS satellites must compensate for time dilation effects, or they'd accumulate errors of about 38 microseconds daily, translating to positioning errors of approximately 10 kilometers per day. What we experience as the steady universal flow of time is actually relative, varying slightly throughout our daily lives without our noticing. The twin paradox illustrates this dramatically. Imagine identical twins, one who stays on Earth while the other travels at near light speed to a distant star and back. Upon return, the traveling twin would be significantly younger than the earthbound twin. From the traveler's perspective, time passed normally, but upon return, they'd find years or decades more had passed on Earth. Both twins experienced time correctly, according to their reference frames, yet they aged at different rates. Time dilation becomes most extreme near the event horizon of a black hole, where gravity is so intense that time nearly stops relative to distant observers. If you could hover just outside a black hole's event horizon, you might experience 1 hour while observers far away would see thousands or millions of years pass. This isn't science fiction, it's the mathematics of general relativity, our most accurate description of how gravity works. What makes time dilation paradoxical is that while each observer experiences time passing normally in their own reference frame, they'll disagree about how much time has passed when they compare notes. There's no universal now that everyone can agree on. Simultaneity itself is relative. Events that appear simultaneous to one observer may occur at different times for another observer, depending on their relative motion. This leads to the ladder paradox, or barn pole paradox. Imagine a runner carrying a pole that's longer than a barn when both are at rest. If the runner moves fast enough, length contraction, another relativistic effect, makes the pole shorter from the barn's perspective. This means the entire pole can momentarily fit inside the barn. But from the runner's perspective, the barn contracts, making it even shorter relative to the pole. How can the pole both fit and not fit inside the barn? The resolution involves understanding that simultaneous events, like the pole's front and back ends being inside the barn, aren't simultaneous in all reference frames. Einstein's breakthrough was realizing that time and space aren't separate, absolute entities, but are woven into a single fabric called space-time. Movement through space affects movement through time. The faster you move through space, the slower you move through time. This unification resolved the paradoxes mathematically, but it still challenges our intuition, which evolved in a low-speed, weak gravity environment where these effects are imperceptible. Time dilation also connects to quantum mechanics in perplexing ways. In quantum field theory, virtual particles constantly pop in and out of existence, but their lifetime depends on how quickly they move. From certain reference frames, some particles might exist for different durations than from other perspectives, raising questions about the fundamental nature of existence itself. The ultimate time paradox emerges near singularities like those at the center of black holes, where our current physics breaks down completely. General relativity predicts that time itself ends at the singularity, while quantum mechanics suggests something else might happen. This incompatibility between our two most successful physical theories points to a deeper understanding of time we haven't yet achieved. Time dilation challenges our notion that time is a river flowing uniformly for everyone. Instead, it's more like a landscape where different observers follow different paths, experiencing time at different rates. This paradox isn't just a curiosity, it's fundamental to how our universe works, affecting everything from particle behavior to the large-scale structure of the cosmos. As we contemplate time dilation, we're forced to acknowledge that our intuitive understanding of time as an absolute universal flow is fundamentally incorrect. The universe operates according to principles that seem paradoxical from our limited human perspective, but are self-consistent within the mathematics of relativity. Time, rather than being the rigid framework within which events occur, is a flexible dimension intimately connected with space, gravity, and motion, a reality far stranger and more fascinating than our everyday experience suggests. The quantum vacuum, far from being empty nothingness, teems with virtual particles that continuously pop in and out of existence following the bizarre rules of quantum mechanics. This quantum foam, as physicists call it, represents one of the most profound paradoxes in physics. Absolute emptiness is impossible. Even in the purest vacuum, stripped of all matter and energy, quantum fluctuations persist, creating and annihilating particle-antiparticle pairs in vanishingly brief moments. These quantum fluctuations aren't merely theoretical constructs. They have measurable effects on the real world. The Casimir effect, first predicted in 1948, demonstrates how quantum vacuum fluctuations can create a tiny but measurable attractive force between parallel metal plates. When the plates are placed extremely close together, they restrict the types of virtual particles that can appear in the space between them, creating a pressure difference that pushes the plates together. This effect, now measured with high precision, provides direct evidence for the reality of quantum vacuum fluctuations. The implications of this perpetual quantum activity extend far beyond laboratory experiments. Hawking radiation, the theoretical process by which black holes slowly evaporate, relies on quantum vacuum fluctuations. When virtual particle pairs appear near a black hole's event horizon, one particle might fall in, while the other escapes, effectively stealing energy from the black hole. Over immense periods, this process could cause even the most massive black holes to eventually disappear. A prediction that creates its own paradoxes about information conservation and the ultimate fate of matter that falls into black holes. Even more remarkably, these quantum vacuum fluctuations might explain the largest structure we know, the universe itself. Some cosmological theories suggest that our entire universe might have emerged as a quantum fluctuation, expanding through inflation into the cosmos we observe today. This would mean that the sum total of all energy in the universe, including the positive energy of matter and the negative energy of gravitational fields, might actually be zero, with our universe representing an elaborate redistribution of nothing. The quantum vacuum also plays a crucial role in particle physics through vacuum polarization. The apparently empty space around particles isn't really empty. It's filled with virtual particles that can affect the properties of real particles. This leads to subtle but measurable effects, such as the Lamb shift in atomic spectra and changes to the magnetic moment of electrons. These quantum vacuum effects must be carefully accounted for in modern particle physics calculations. Perhaps most intriguingly, quantum vacuum fluctuations might hold the key to understanding dark energy, the mysterious force causing our universe's expansion to accelerate. Initial calculations of vacuum energy suggested a value 120 orders of magnitude larger than observed, creating what physicists call the vacuum catastrophe. This enormous discrepancy between theory and observation remains one of physics' greatest unsolved puzzles, suggesting our understanding of the quantum vacuum remains incomplete. The quantum vacuum also challenges our understanding of causality. According to the uncertainty principle, energy can be borrowed from the vacuum for very brief periods, allowing particles to temporarily tunnel through energy barriers they classically couldn't cross. This quantum tunneling happens faster than light, could travel the same distance, seeming to violate causality. However, careful analysis shows that no useful information can be transmitted this way, preserving Einstein's cosmic speed limit while highlighting the peculiar nature of quantum processes. Recent experiments have even demonstrated that the quantum vacuum can be squeezed, reducing fluctuations in one property, while increasing them in another. This quantum squeezing has practical applications in improving the sensitivity of gravitational wave detectors, allowing us to observe cosmic events like black hole mergers with unprecedented precision. The fact that we can manipulate the supposedly empty vacuum to enhance our measurements reveals how deeply quantum effects are woven into the fabric of reality. These vacuum fluctuations also raise profound questions about the nature of reality itself. If empty space is never truly empty, and virtual particles constantly flicker in and out of existence, what does this tell us about the fundamental structure of the universe? Some theorists suggest that space itself might be discrete at the smallest scales, with quantum foam representing the fundamental graininess of space-time. This discreteness could help resolve some of the infinities that plague quantum field theories, but it would mean that our perception of space as a smooth, continuous medium is yet another approximation that breaks down at the quantum level. The paradox of the quantum vacuum forces us to confront the limitations of our classical intuitions. The very concept of nothing becomes problematic in a quantum universe. True nothingness appears to be physically impossible, replaced by a dynamic quantum void that underlies and influences everything we observe. As we continue to probe these quantum depths, we're discovering that the seemingly empty space between particles might hold the key to understanding the deepest mysteries of our universe. Quantum teleportation represents one of the most remarkable manifestations of quantum mechanics, demonstrating how information can be transmitted in ways that seem to defy classical physics. Unlike the science fiction concept of teleportation, quantum teleportation doesn't involve moving matter through space. Instead, it transfers the quantum state of one particle to another particle at a distant location, using entanglement as the mechanism for transmission. The process relies on what physicists call quantum information, the complete quantum state of a particle, including properties like spin, polarization, or energy level. Unlike classical information, quantum information cannot be perfectly copied due to the no-cloning theorem, another fundamental restriction that emerges from quantum mechanics. This limitation might seem like a drawback, but it's actually crucial for quantum cryptography, ensuring that quantum communications cannot be intercepted without detection. What makes quantum teleportation particularly paradoxical is its relationship with classical information transmission. While the quantum state is instantaneously transmitted between entangled particles, the process still requires the transmission of classical information, typically through conventional communication channels limited by the speed of light, to complete the teleportation. This creates a subtle interplay between quantum and classical information that challenges our understanding of causality and information flow. The mathematics behind quantum teleportation reveals another paradox. The quantum information being teleported never travels through the space between the sender and receiver. Instead, the pre-existing entanglement between particles serves as a kind of information channel that transcends space. This has led some physicists to suggest that quantum information might exist in a different type of space altogether, a quantum configuration space that operates according to different rules than our familiar three-dimensional world. Recent experiments have pushed the boundaries of quantum teleportation to new extremes. Scientists have successfully teleported quantum states between particles separated by dozens of kilometers, and even between ground stations and satellites in orbit. These achievements aren't merely technical triumphs. They're demonstrations of quantum mechanics' most counterintuitive predictions operating at macroscopic scales. The implications of quantum teleportation extend far beyond practical applications in quantum computing and cryptography. The process raises fundamental questions about the nature of information itself. In classical physics, information is always encoded in physical systems, patterns of atoms, electromagnetic waves, or other material carriers. But quantum teleportation suggests that quantum information has a more abstract existence, independent of any particular physical embodiment. This connects to a deeper paradox in quantum mechanics known as the state vector collapse. When a quantum system is measured, its wave function, the mathematical description of its quantum state, instantaneously collapses into a definite classical state. This collapse appears to happen simultaneously across all space, raising questions about how information about the measurement result propagates. Quantum teleportation provides a concrete framework for studying how quantum information moves and transforms, offering insights into this fundamental mystery. The relationship between quantum teleportation and entropy, a measure of disorder and information content, reveals additional paradoxes. While classical information transmission always increases the total entropy of the universe, quantum teleportation can seemingly circumvent this restriction in certain cases. This suggests that quantum information might operate according to different thermodynamic principles than classical information, hinting at deeper connections between quantum mechanics and thermodynamics. Perhaps most intriguingly, quantum teleportation experiments have begun to probe the intersection between quantum mechanics and gravity. When quantum states are teleported between locations at different gravitational potentials, relativistic effects must be taken into account. The quantum states experience time dilation just like classical objects, but they maintain their quantum coherence throughout the process. This raises the possibility of using quantum teleportation as a tool for studying quantum gravity, the long-sought unification of quantum mechanics and general relativity. The success of quantum teleportation also challenges our intuitions about locality and separability. Classical physics assumes that objects have definite properties independent of measurement, and that distant objects are truly separate. Quantum teleportation, along with other quantum phenomena like entanglement, suggests that these assumptions break down at the quantum level. The universe appears to be fundamentally non-local, with quantum states that can't be fully described by local properties alone. As we develop more sophisticated quantum technologies, these paradoxes move from the realm of theoretical physics into practical engineering challenges. Quantum teleportation is expected to play a crucial role in quantum networks, the quantum analog of classical internet infrastructure. Building such networks requires reconciling the strange behavior of quantum systems with the classical world we inhabit, forcing us to confront these paradoxes, not just philosophically, but in concrete technological implementations. The holographic principle stands as one of the most revolutionary ideas in modern physics, suggesting that our three-dimensional reality might be encoded on a two-dimensional boundary, much like a hologram. This principle emerged from studies of black hole thermodynamics, but has expanded to challenge our most basic assumptions about space, dimension, and the nature of reality itself. The story begins with black holes and a startling calculation by physicist Jacob Bekenstein, who discovered that a black hole's entropy, a measure of its information content, is proportional not to its volume, as one might expect, but to its surface area. This seemingly impossible result suggests that all the information about objects that fall into a black hole must somehow be encoded on its two-dimensional event horizon, like information stored on a cosmic hard drive. This insight led theoretical physicist Leonard Susskind to propose the holographic principle. In any region of space, the total amount of information that can be stored is limited not by the region's volume, but by its surface area. This means that everything happening in a three-dimensional volume can be completely described by information encoded on its two-dimensional boundary. The mathematics supporting this principle has been rigorously developed through string theory and quantum gravity research, particularly through Juan Maldacena's ADS-CFT correspondence. The implications are staggering. If the holographic principle is correct, then our experience of living in a three-dimensional world might be an elaborate illusion, a projection of information stored on a distant cosmic boundary. This doesn't mean our three-dimensional experience isn't real, but rather that it emerges from a more fundamental two-dimensional description, just as the three-dimensional image in a hologram emerges from information encoded on a flat surface. Recent experimental work has begun to find hints of holographic behavior in unexpected places. Quantum many-body systems, collections of particles that interact according to quantum mechanical rules, sometimes display patterns that can be better understood using holographic descriptions. For instance, certain types of quantum entanglement in materials like quantum spin chains show properties that mirror gravitational systems in higher dimensions, suggesting deep connections between quantum mechanics, gravity, and dimensionality. The holographic principle also offers new perspectives on the quantum measurement problem. If our three-dimensional reality is encoded on a two-dimensional boundary, then quantum wave function collapse might be better understood as a change in how information is organized on this boundary, rather than a physical process in three-dimensional space. This reframing could help resolve some of the paradoxes associated with quantum measurement and wave function collapse. One particularly fascinating application of holographic thinking comes from cosmology. Some theorists propose that the early universe underwent a period of holographic cosmology, where three-dimensional space emerged from a two-dimensional description through a process similar to holographic projection. This could help explain the uniformity of cosmic microwave background radiation and other puzzling features of the early universe. The principle has profound implications for quantum computing as well. If information in our universe is fundamentally bounded by surface area rather than volume, this could impose fundamental limits on quantum computation that we haven't yet encountered. However, it might also suggest new approaches to quantum computing that exploit holographic relationships between different dimensional descriptions of the same system. Researchers are now exploring connections between the holographic principle and quantum error correction, the techniques used to protect quantum information from decoherence. The way information is redundantly encoded in holographic systems bears striking similarities to quantum error-correcting codes, suggesting that nature might use similar strategies to maintain quantum coherence in gravitational systems. The holographic principle also intersects with theories about the origin of gravity itself. In this view, gravity might not be a fundamental force, but rather an emergent phenomenon, a consequence of how information is organized in holographic systems. This perspective has led to new approaches in quantum gravity research, suggesting ways to reconcile quantum mechanics with general relativity. Perhaps most intriguingly, the holographic principle raises questions about the nature of space and time themselves. If our three-dimensional reality can be completely described by information on a two-dimensional boundary, then space itself might not be fundamental, but rather emergent from more basic quantum mechanical principles. This could mean that space and time are not the foundation of reality, but rather consequences of how quantum information is organized at a more fundamental level. Quantum field theory presents us with one of the most successful yet paradoxical frameworks in physics, describing a universe where particles are not fundamental objects, but rather excitations in underlying fields that permeate all of space. This perspective transforms our understanding of matter and forces, revealing a reality where particles can spontaneously appear from seemingly nothing, where empty space carries enormous energy, and where the very notion of a particle becomes, surprisingly, ambiguous. The particle-field duality introduces profound paradoxes about the nature of reality. Consider an electron. In quantum field theory, it's not a discrete particle, but a localized excitation in the electron field, a ripple in an invisible ocean that extends throughout the universe. This means that what we perceive as distinct particles are actually manifestations of the same underlying field, challenging our intuitive notion of individual objects. One of the most perplexing aspects of quantum field theory emerges in the calculation of vacuum energy. The theory predicts that even empty space contains an infinite amount of energy from quantum fluctuations in various fields. Physicists use a mathematical technique called renormalization to handle these infinities, effectively subtracting infinity from infinity to get finite, measurable results. While this approach works remarkably well, in practice, it raises deep questions about the physical meaning of these infinite quantities and whether our mathematical framework is truly capturing the fundamental nature of reality. The concept of particle creation and annihilation in quantum field theory presents another paradox. When particles collide with sufficient energy, they can create new particles that didn't exist before, not by breaking apart existing matter, but by converting pure energy into mass through Einstein's famous equation E equals mc squared. This process seems to violate our intuitive understanding of conservation laws, though it actually preserves them in subtle ways. The reverse process, where particles annihilate into pure energy, equally challenges our classical intuitions about the permanence of matter. Quantum field theory also introduces the concept of virtual particles, temporary fluctuations in quantum fields that can never be directly observed, but whose effects are measurable. These virtual particles can briefly violate energy conservation, borrowing energy from the quantum vacuum for extremely short periods allowed by the uncertainty principle. This violation of conservation laws, though temporary, suggests that at the quantum level, even our most sacred physical principles might hold only statistically rather than absolutely. The theory reveals surprising connections between seemingly unrelated phenomena through what physicists call crossing symmetry. The mathematics shows that a particle scattering process viewed in one reference frame can appear as particle creation or annihilation when viewed from another frame. This symmetry suggests a deep unity in particle interactions that transcends our usual categorizations of physical processes. Perhaps most puzzling is the role of the observer in quantum field theory. The very concept of a particle becomes observer-dependent. What one observer sees as particles, another observer in a different reference frame might see as a complicated mixture of different particles. This relativistic quantum effect, known as the Unruh effect, predicts that an accelerating observer will detect particles in what an inertial observer considers empty space, suggesting that the particle content of the universe isn't absolute, but depends on the observer's state of motion. The theory also predicts phenomena like quantum entanglement between fields, where excitations in different quantum fields become correlated in ways that can't be explained by classical physics. This field entanglement is more fundamental than particle entanglement, suggesting that the quantum correlations we observe between particles are actually manifestations of deeper connections between the underlying fields. Recent developments in quantum field theory have revealed even more paradoxes through the study of quantum fields in curved space-time. Near black holes, the very definition of particles becomes ambiguous, as different observers will disagree not just about particle properties, but about whether particles exist at all. This ambiguity touches on fundamental questions about the nature of reality and the role of the observer in quantum physics. The interaction between quantum fields and gravity remains one of physics' greatest unsolved puzzles. While quantum field theory works brilliantly for particle physics, combining it with general relativity leads to mathematical inconsistencies. These problems suggest that our current understanding of quantum fields might be an approximation of a more fundamental theory that coherently describes both quantum mechanics and gravity. The quantum measurement problem stands as one of the most enigmatic paradoxes in physics, touching on fundamental questions about consciousness, reality, and the boundary between the quantum and classical worlds. While quantum mechanics perfectly describes the evolution of isolated quantum systems through the Schrödinger equation, the act of measurement appears to trigger a sudden, non-deterministic collapse of the wave function that cannot be described by the same equation. This apparent breakdown in quantum mechanical description during measurement has led to numerous interpretations, each attempting to resolve the paradox in different ways. The Copenhagen interpretation, historically the most widely accepted, simply postulates that measurement causes wave function collapse, but doesn't explain how or why this happens. This pragmatic approach works well for calculations, but leaves deep philosophical questions unanswered. Quantum decoherence offers a more modern perspective on this paradox. Rather than viewing measurement as a mysterious collapse, decoherence theory suggests that quantum systems gradually lose their quantum properties through inevitable interactions with their environment. These interactions effectively measure the system continuously, causing quantum superpositions to appear to collapse into classical states. The mathematics of decoherence reveals something remarkable. Quantum information isn't truly lost during this process, but becomes spread out across countless environmental degrees of freedom. The quantum state still exists in principle, but it becomes practically impossible to access or measure, appearing to us as a classical outcome. This suggests that the quantum to classical transition might be more about information distribution than actual physical collapse. Recent experiments have begun to probe this boundary between quantum and classical behavior with unprecedented precision. Scientists can now observe the gradual decoherence of quantum systems in real time, watching as quantum superpositions slowly transform into classical mixtures. These experiments reveal that decoherence isn't instantaneous but proceeds through measurable intermediate states, challenging the traditional notion of sudden wave function collapse. One particularly fascinating aspect of decoherence theory is its relationship with quantum Darwinism. This framework suggests that only quantum states robust enough to survive environmental interaction and create multiple records in the environment become the classical reality we observe. In this view, the classical world emerges through a kind of natural selection process operating on quantum states, where only the fittest states survive to be observed. The role of the observer in quantum mechanics takes on new meaning through decoherence theory. Rather than consciousness playing a special role in collapsing wave functions, observers simply become part of the large environmental system that interacts with quantum states. This removes the need for consciousness to play a fundamental role in quantum mechanics, though it doesn't completely resolve questions about the nature of observation and reality. Quantum protective measurement, a relatively new experimental technique, adds another layer to this paradox. These measurements can extract information about quantum states without apparently collapsing them, suggesting that the traditional view of measurement-induced collapse might be oversimplified. This raises questions about what truly constitutes a measurement and whether different types of measurements might affect quantum systems in fundamentally different ways. The emergence of classicality through decoherence connects to deeper questions about the arrow of time. The apparent irreversibility of wave function collapse mirrors the thermodynamic arrow of time, suggesting connections between quantum measurement, entropy increase, and the flow of time itself. Some physicists propose that decoherence might provide a quantum mechanical origin for the direction of time we experience. Decoherence theory also offers insights into quantum computing challenges. The main obstacle to building practical quantum computers isn't just technical precision, but fighting decoherence, preventing quantum bits from interacting with their environment long enough to perform calculations. Understanding decoherence has led to quantum error correction techniques that might eventually allow us to build fault-tolerant quantum computers. The measurement problem intersects with questions about quantum entanglement in intriguing ways. When entangled particles decohere through interaction with their environment, their quantum correlations don't simply disappear, but become encoded in environmental degrees of freedom. This suggests that quantum correlations might play a more fundamental role in structuring reality than previously thought, even if they become hidden from direct observation. Quantum contextuality represents one of the most subtle yet profound paradoxes in quantum mechanics, suggesting that the properties we measure in quantum systems don't exist independently of how we choose to measure them. This principle goes beyond the usual uncertainty relations, revealing that even properties we might think could be measured simultaneously are actually dependent on the full experimental context in which they're observed. The Cauchy-Specker theorem, which formally proves quantum contextuality, demonstrates that it's impossible to assign definite values to all quantum observables in a way that's independent of measurement context. This means that quantum properties aren't simply hidden variables waiting to be revealed. They don't exist in a definite form until the measurement context is specified. This contradicts our classical intuition that objects possess inherent properties, regardless of how we observe them. Consider a quantum system where we can measure different properties, like spin along various axes. Classical physics would suggest that these properties exist simultaneously, even if we can't measure them all at once. However, quantum contextuality shows that the value we measure for one property can depend on which other properties we choose to measure simultaneously. It's as if the quantum system responds not just to what we measure, but to our entire experimental arrangement. Recent experiments have demonstrated quantum contextuality in increasingly sophisticated ways. One particularly striking demonstration uses sequential measurements on single quantum systems to show how the outcome of a measurement can depend on the sequence of other measurements performed. These experiments reveal that quantum contextuality isn't just a theoretical curiosity, but a fundamental aspect of how quantum systems behave. The implications of contextuality extend beyond individual quantum systems to quantum networks and computation. Quantum contextuality has been identified as a key resource for quantum computational advantage, the ability of quantum computers to outperform classical ones on certain tasks. This suggests that contextuality might be one of the fundamental features that gives quantum computation its power. Contextuality also intersects with quantum non-locality in fascinating ways. While non-locality deals with correlations between spatially separated systems, contextuality reveals non-classical behavior even in single quantum systems. Together, these phenomena suggest that quantum mechanics requires us to abandon not just locality, but also the very idea that physical properties have observer-independent reality. The experimental verification of contextuality has important implications for quantum foundations. It rules out certain types of hidden variable theories that might otherwise explain quantum behavior through classical-like mechanisms. This strengthens the case that quantum mechanics represents a fundamental departure from classical physics, not just an incomplete description of a more classical reality. New research has begun to explore connections between contextuality and other quantum phenomena like entanglement and discord. Some studies suggest that contextuality might be more fundamental than entanglement, providing a deeper explanation for various non-classical behaviors observed in quantum systems. This perspective could help unify our understanding of different quantum resources and their applications in quantum technologies. Quantum contextuality also raises important questions about the nature of reality itself. If quantum properties don't exist independently of how we measure them, what does this mean for the objective reality of the physical world? Some philosophers and physicists suggest that we might need to abandon the idea of observer-independent reality altogether accepting instead a more nuanced view where reality emerges through the interaction between quantum systems and their measurement contexts. The relationship between contextuality and quantum logic provides another fascinating angle. Traditional logic assumes that propositions about physical systems have truth values independent of other propositions we might consider. Quantum contextuality challenges this assumption, suggesting we might need a fundamentally different logical framework to describe quantum reality accurately. Recent theoretical work has extended the concept of contextuality beyond quantum mechanics to more general probabilistic theories. This research suggests that contextuality might be a generic feature of theories that go beyond classical physics, providing insights into what kinds of physical theories might be possible and what constraints they must satisfy. The intersection of quantum mechanics and thermodynamics reveals some of the most profound paradoxes in physics, particularly concerning the nature of time's arrow and the flow of information in the universe. While quantum mechanics is fundamentally reversible at the microscopic level, our macroscopic world displays an unmistakable direction of time through the increase of entropy. This tension between microscopic reversibility and macroscopic irreversibility presents a deep puzzle about the nature of time itself. Maxwell's demon, a famous thought experiment, takes on new significance in the quantum realm. This hypothetical intelligent being could seemingly violate the second law of thermodynamics by sorting molecules based on their velocities, creating order from disorder without expending energy. However, quantum mechanics shows that the act of measurement itself carries an entropy cost, preventing the demon from actually decreasing the total entropy of the system. This connection between information and entropy becomes even more intricate when quantum effects are considered. Recent experiments in quantum thermodynamics have revealed surprising behaviors in nanoscale systems. When quantum systems are driven out of equilibrium, they can exhibit fluctuations that apparently violate the second law of thermodynamics temporarily, though the law holds on average. These quantum fluctuation theorems suggest that thermodynamic laws might need refinement at the quantum scale, where energy and information become increasingly interchangeable. The concept of quantum heat engines pushes this understanding further. Unlike classical heat engines, quantum engines can exploit quantum coherence and entanglement to achieve efficiencies beyond classical limits. This suggests that quantum effects might allow us to extract work from systems in ways that seem to challenge traditional thermodynamic principles, though deeper analysis shows these processes remain consistent with fundamental physical laws. Quantum thermal machines also demonstrate peculiar behaviors regarding the direction of heat flow. In certain quantum systems, heat can flow from cold to hot regions temporarily, seemingly violating the traditional understanding of the second law. These apparent violations are reconciled through careful consideration of quantum correlations and the role of information in thermodynamic processes. The relationship between quantum entanglement and thermodynamic entropy presents another fascinating paradox. While entropy typically increases as systems become more disordered, the creation of quantum entanglement can actually decrease certain measures of entropy locally, though the total entropy of the universe still increases. This suggests a deep connection between quantum information and thermodynamic behavior that we're only beginning to understand. Recent theoretical work has explored the concept of quantum time crystals, systems that spontaneously break time translation symmetry, exhibiting periodic behavior in their ground state. These structures seem to challenge our understanding of thermodynamic equilibrium and the arrow of time, suggesting that certain quantum systems might naturally evolve through repeated cycles without requiring energy input. The quantum Zeno effect adds another layer to these thermodynamic paradoxes. Continuous observation of a quantum system can freeze its evolution, preventing transitions that would normally occur. This raises questions about the relationship between measurement, entropy, and the flow of time in quantum systems. If observation can halt quantum evolution, what does this tell us about the nature of time at the quantum level? Quantum thermodynamics also reveals surprising connections to black hole physics through the concept of entanglement entropy. The entropy of black holes, proportional to their surface area rather than volume, suggests that information and entropy might be fundamentally holographic properties. This connection between quantum information, thermodynamics, and gravity hints at deeper principles underlying all of physics. The emergence of classical thermodynamic behavior from quantum systems remains a central mystery, while decoherence explains how quantum superpositions become effectively classical. The emergence of irreversibility and the arrow of time from fundamentally reversible quantum mechanics is still not fully understood. This suggests our understanding of both quantum mechanics and thermodynamics might be incomplete. These paradoxes in quantum thermodynamics have practical implications for quantum computing and quantum information processing. Understanding how quantum systems exchange energy and information with their environment is crucial for developing quantum technologies that can maintain coherence long enough to perform useful computations. The interplay between quantum effects and thermal noise represents both a fundamental challenge and an opportunity for quantum engineering. The relationship between quantum mechanics and chaos theory presents one of physics' most intriguing paradoxes. While classical systems can exhibit chaos, extreme sensitivity to initial conditions, quantum systems are governed by the Schrödinger equation, which is linear and deterministic. This fundamental tension between classical chaos and quantum behavior raises deep questions about the nature of complexity in the universe. Quantum chaos emerges in systems where the classical limit would display chaotic behavior. However, the quantum version of these systems behaves quite differently. The uncertainty principle prevents quantum systems from having precisely defined initial conditions, and the wave-like nature of quantum mechanics means that quantum systems can't follow the infinitely precise trajectories that characterize classical chaos. This leads to the phenomenon of quantum scarring, patterns in quantum wave functions that trace the paths of unstable periodic orbits in the corresponding classical system. These scars represent a kind of quantum memory of classical chaos, showing how quantum mechanics preserves information about classical behavior in unexpected ways. Recent experiments have observed these scars in atomic systems and quantum dots, providing direct evidence of this quantum classical correspondence. The concept of quantum ergodicity adds another layer to this paradox. Classical chaotic systems are ergodic, meaning they eventually explore all possible states with equal probability. Quantum systems, however, can exhibit anti-ergodic behavior, remaining localized in certain states much longer than classical mechanics would predict. This quantum many-body localization challenges our understanding of how complex systems approach equilibrium. Quantum complexity theory reveals even deeper paradoxes. While classical computers struggle to simulate quantum systems due to their exponential complexity, the quantum systems themselves evolve effortlessly according to simple physical laws. This suggests that nature possesses computational capabilities far beyond our classical computers, raising questions about the relationship between physical reality and computation. The scrambling of quantum information in complex systems leads to fascinating phenomena like the butterfly effect in quantum systems. Unlike classical chaos, where information is truly lost through exponential sensitivity to initial conditions, quantum information is never really lost. It becomes scrambled in increasingly complex quantum correlations. This preservation of information while appearing to lose it represents a fundamental paradox in quantum complexity. Recent research has explored connections between quantum chaos and black hole physics through the concept of quantum scrambling. Black holes appear to be nature's fastest scramblers of quantum information, suggesting deep connections between gravity, quantum chaos, and information theory. The study of these connections has led to new theoretical tools like out-of-time order correlators, which measure how quickly quantum systems develop complex correlations. The emergence of classicality in complex quantum systems presents another paradox. While individual quantum particles can exist in superpositions, large collections of particles typically behave classically. This quantum to classical transition isn't fully understood, particularly in systems where quantum effects and chaos compete. Some theories suggest that decoherence and chaos work together to produce classical behavior, but the exact mechanism remains mysterious. Quantum complexity also manifests in the phenomenon of quantum phase transitions at zero temperature. Unlike classical phase transitions driven by thermal fluctuations, quantum phase transitions are driven by quantum fluctuations and can occur even at absolute zero. These transitions can create long-range quantum correlations that challenge our understanding of how complex order emerges in quantum systems. The study of quantum networks and complex quantum systems has revealed surprising properties like quantum synchronization, where multiple quantum systems can spontaneously align their behavior through quantum correlations. This quantum coherence in complex systems seems to defy the tendency toward chaos and decoherence, suggesting mechanisms for maintaining quantum order that we're only beginning to understand. The relationship between quantum complexity and consciousness presents particularly fascinating questions. Some theories propose that consciousness might emerge from quantum coherence in neural networks, while others suggest that quantum effects are too fragile to play a role in brain function. This debate touches on fundamental questions about the nature of consciousness and its relationship to quantum mechanics. Quantum cosmology presents us with perhaps the most mind-bending paradoxes of all, as it attempts to apply quantum mechanics to the entire universe. When we try to describe the cosmos itself as a quantum system, we encounter profound questions about the nature of existence, the role of observation, and the meaning of probability when there's no external observer to collapse the wave function. The Wheeler-DeWitt equation, often called the wave function of the universe, attempts to describe the quantum state of the entire cosmos. However, this leads to the problem of time. The equation suggests that the universe's wave function is static, unchanging, yet we experience time flowing and the universe evolving. This timeless quantum description versus our temporal experience represents one of the deepest paradoxes in physics. Eternal inflation theory suggests that our universe might be just one bubble in an infinitely expanding multiverse, where quantum fluctuations continuously spawn new universes. In this picture, quantum effects don't just create particles from the vacuum, they create entire universes. This raises profound questions about probability and prediction in an infinite multiverse, where everything that can happen does happen an infinite number of times. The quantum origin of our universe presents another paradox. The Big Bang appears to have emerged from a quantum fluctuation, but quantum mechanics requires an observer to collapse wave functions into definite states. Who, or what, observed the universe into existence? Some theorists suggest that decoherence might resolve this paradox, with different parts of the quantum universe effectively observing each other, but the details remain controversial. Recent developments in quantum cosmology have introduced the concept of quantum gravity, where space itself emerges from fundamental quantum interactions. In this theory, space isn't a continuous background, but a network of quantum relationships that can undergo phase transitions. At high energies, the very notion of space and distance might break down, replaced by a more fundamental quantum description. The cosmological constant problem takes on new dimensions in quantum cosmology. Quantum field theory predicts a vacuum energy density enormously larger than what we observe. This discrepancy suggests either a fundamental flaw in our understanding of quantum vacuum energy or the existence of some unknown mechanism that almost perfectly cancels out these quantum contributions. String theory and loop quantum gravity offer competing approaches to quantum cosmology, each with its own paradoxes. String theory suggests extra dimensions and multiple possible vacuum states, leading to a vast landscape of possible universes. Loop quantum gravity proposes that space itself is quantized at the Planck scale, with quantum geometry giving rise to classical space-time through a process we're still trying to understand. The holographic principle in cosmology suggests that the information content of our entire universe might be encoded on its boundary, like a cosmic version of a hologram. This raises questions about the nature of space, time, and locality in quantum gravity. If our three-dimensional universe is encoded in two dimensions, what does this mean for causality and the flow of time? Quantum entanglement across cosmic scales presents another fascinating paradox. If quantum correlations were established in the early universe, these entangled states might persist across billions of light years, creating a cosmic web of quantum relationships. Some theories suggest that these primordial quantum correlations might explain aspects of cosmic structure we observe today. The role of quantum measurement in cosmology becomes particularly puzzling when considering the multiverse. If quantum mechanics requires measurement to produce definite outcomes, how do we interpret quantum events in parts of the multiverse that can never be observed? This leads to questions about the reality of unobservable regions of the cosmos and the meaning of quantum mechanics in their description. The arrow of time in quantum cosmology presents unique challenges. While local quantum systems can exhibit time symmetry, the universe as a whole shows a clear temporal direction through cosmic expansion and entropy increase. Reconciling this cosmological arrow of time with quantum mechanics remains one of physics' great unsolved problems. The emergence of quantum effects in biological systems presents a fascinating new frontier in physics, challenging our understanding of both quantum mechanics and life itself. While quantum mechanics typically dominates at microscopic scales and ultra-cold temperatures, growing evidence suggests that quantum phenomena play crucial roles in biological processes, from photosynthesis to bird navigation, raising profound questions about the boundary between quantum and classical behavior in living systems. Quantum coherence in photosynthesis represents one of the most striking examples of quantum biology. Plants and certain bacteria achieve near-perfect efficiency in converting sunlight into chemical energy by maintaining quantum coherence in their light-harvesting complexes. This coherence allows energy to explore multiple paths simultaneously, finding the most efficient route to reaction centers. The paradox lies in how these quantum effects persist in warm, wet, and noisy biological environments where quantum coherence should rapidly decay. The quantum compass of migratory birds presents another biological quantum paradox. Evidence suggests that birds use quantum entanglement in cryptochrome proteins to detect Earth's magnetic field for navigation. These proteins maintain quantum coherence long enough to respond to magnetic fields, despite operating at body temperature. This challenges our understanding of quantum decoherence and suggests that biological systems might have evolved to protect and exploit quantum effects. Enzyme catalysis may also exploit quantum tunneling to accelerate chemical reactions. Classical physics suggests that chemical reactions require sufficient energy to overcome activation barriers, but quantum tunneling allows particles to pass through these barriers. Some enzymes appear to enhance tunneling rates, suggesting that life has evolved to harness quantum effects for essential biochemical processes. This raises questions about the role of quantum mechanics in the evolution of life itself. The quantum nature of smell presents another biological paradox. Traditional theories suggest that molecular shape determines odor, but growing evidence indicates that smell might involve quantum effects. Electrons tunneling between different molecular configurations could explain why molecules with identical shapes can smell different, and why mirror image molecules sometimes have distinct odors. This suggests that our sensory experiences might directly reflect quantum phenomena. Quantum effects in DNA mutation and repair introduce even more profound questions. Quantum tunneling of protons between DNA base pairs could initiate mutations, while quantum coherence might play a role in DNA repair mechanisms. This suggests that quantum mechanics might influence evolution itself, raising philosophical questions about the relationship between quantum indeterminacy and biological destiny. The emergence of consciousness presents, perhaps, the deepest paradox in quantum biology. Some theories propose that quantum processes in microtubules within neurons could generate consciousness, potentially explaining how subjective experience emerges from physical processes. While controversial, these ideas highlight the challenge of understanding how quantum phenomena might scale up to influence macroscopic biological functions. Biological quantum computation represents another frontier. Some researchers suggest that living systems might perform quantum computations as part of their normal function. If true, this would imply that nature solved the problem of quantum computation long before humans conceived of it, raising questions about what other quantum capabilities might be hidden in biological systems. The role of quantum effects in molecular motors and protein folding adds another layer of complexity. These fundamental biological processes occur at scales where quantum effects become relevant, yet they must reliably produce classical outcomes. Understanding how biological systems navigate this quantum to classical transition could provide insights into both quantum mechanics and the nature of life. The concept of quantum Darwinism in biological systems suggests that only quantum states robust enough to survive environmental interaction become observable classical states. This might explain how biological systems maintain quantum coherence long enough to exploit it while still producing reliable classical outcomes. The interplay between quantum mechanics and natural selection could represent a fundamental principle in the organization of life. Recent research has begun to explore quantum networks in biological systems, suggesting that living organisms might utilize networks of quantum coherent processes. These networks could explain how biological systems achieve their remarkable efficiency and precision. But they raise questions about how such delicate quantum effects could be maintained in complex biological environments. The relationship between quantum information and causality presents some of the most perplexing paradoxes in modern physics. While classical information flows linearly through time, quantum information exhibits behaviors that seem to defy our conventional understanding of cause and effect. These quantum violations of causality force us to reconsider fundamental assumptions about the nature of information and its relationship with time. The delayed choice quantum eraser experiment stands as one of the most striking demonstrations of quantum causality violation. In this experiment, the decision to measure which path a particle took can be made after the particle has already been detected, seemingly allowing future choices to influence past events. This apparent retrocausality challenges our intuitive understanding of temporal order and raises profound questions about the nature of time itself. Quantum information demonstrates peculiar properties when it comes to copying and deletion. The no-cloning theorem states that it's impossible to create perfect copies of unknown quantum states, while the no-deleting theorem indicates that quantum information cannot be perfectly erased. Together, these principles suggest that quantum information follows fundamentally different rules than classical information, with implications for both practical quantum computing and our understanding of information conservation in physics. The concept of quantum discord reveals subtle quantum correlations that persist even in the absence of entanglement. This suggests that quantum information has more complex structure than previously thought, with different types of quantum correlations exhibiting different behaviors under measurement and environmental interaction. Understanding these correlations becomes crucial for quantum computing and quantum communication protocols. Quantum teleportation presents another causality paradox. While no information travels faster than light during teleportation, the process seems to involve instantaneous collapse of quantum states across arbitrary distances. This raises questions about how quantum information propagates through space-time, and whether Our classical notions of information transmission need revision in the quantum realm. The holographic principle applied to quantum information suggests that the information content of a region of space might be encoded on its boundary. This creates paradoxes about locality and causality. How can events in the bulk of a region be immediately reflected on its boundary without violating causality? These questions become particularly acute when considering quantum information in gravitational systems. Recent developments in quantum error correction have revealed surprising connections between quantum information and geometry. The way quantum information is protected against errors seems to mirror how space-time geometry emerges in certain theories of quantum gravity. This suggests deep connections between information, causality, and the structure of space-time itself. The concept of quantum computational supremacy raises new paradoxes about the relationship between physical reality and computation. If quantum computers can solve certain problems exponentially faster than classical computers, what does this tell us about the fundamental nature of information processing in our universe? Some theorists suggest that quantum computation might be revealing fundamental limits on how information can be processed in physical systems. Quantum contextuality in information processing presents another layer of paradox. The fact that quantum measurements can depend on the context in which they're performed suggests that quantum information isn't simply stored in systems waiting to be revealed, but is fundamentally shaped by how we choose to measure it. This challenges our understanding of objective reality and the nature of information itself. The emergence of time from quantum information provides yet another paradox. Some theories suggest that time itself might emerge from more fundamental quantum informational processes, rather than being a basic framework in which those processes occur. This would mean that causality and temporal order are emergent phenomena, not fundamental features of reality. Recent experiments with quantum switches, where the order of quantum operations can be placed in superposition, further challenge our understanding of causality. These devices can process quantum information in a way that makes it impossible to say which operation happened first, suggesting that temporal order itself might be quantum mechanical in nature. The frontier of quantum metrology reveals paradoxes that challenge our fundamental understanding of measurement and precision in physics. While classical physics suggests that measurement precision can be improved indefinitely with better instruments, quantum mechanics imposes fundamental limits on measurement accuracy. These quantum limits arise not from technical limitations, but from the inherent nature of reality itself. The standard quantum limit, also known as the shot-noise limit, represents a fundamental boundary in measurement precision that emerges from quantum uncertainty. However, quantum metrology reveals that this limit can be surpassed using quantum resources like entanglement and squeezing. This creates a paradox. How can quantum effects, which typically introduce uncertainty, be used to achieve greater precision than classical methods? Quantum sensing with single atoms pushes these paradoxes further. Individual atoms can be used as exquisitely sensitive probes of electric and magnetic fields, but the act of measurement inevitably disturbs the atom's quantum state. This leads to a delicate balance between gaining information and maintaining quantum coherence, revealing fundamental trade-offs in quantum measurement that have no classical counterpart. The concept of weak measurement introduces another layer of paradox. These measurements, which barely disturb the quantum system, can sometimes yield results that lie outside the expected range of values for the measured property. These weak values challenge our understanding of what measurement means in quantum mechanics and suggest that quantum systems might harbor information in subtle ways we're only beginning to understand. Quantum illumination presents a particularly fascinating paradox in metrology. By using entangled photons, it's possible to detect objects in noisy environments with greater sensitivity than classical methods would allow. Remarkably, this quantum advantage persists even when the entanglement appears to be destroyed by environmental noise, suggesting that quantum correlations can survive in forms we don't fully understand. The quantum Zeno effect in precision measurement creates another paradox. Continuous observation of a quantum system can freeze its evolution, preventing transitions that would normally occur. This effect has practical applications in quantum metrology, but raises deep questions about the nature of time and measurement in quantum mechanics. If observation can halt quantum evolution, what does this tell us about the relationship between measurement and time? Heisenberg's microscope thought experiment takes on new relevance in modern quantum metrology. While originally used to illustrate the uncertainty principle, new techniques like quantum imaging and ghost imaging reveal that the trade-offs between position and momentum measurement are more subtle than initially thought. These techniques suggest ways to extract information about quantum systems that seem to circumvent traditional measurement limitations. The role of quantum back reaction in precision measurement presents another paradox. When measuring extremely precise quantities, the quantum nature of the measuring device itself becomes important. The act of measurement creates quantum entanglement between the measuring device and the system being measured, leading to fundamental limits on measurement precision that arise from quantum mechanics itself. Quantum metrology in gravitational systems reveals even deeper paradoxes. Attempts to measure extremely small distances or times run into fundamental limits where quantum mechanics and gravity become inseparable. These Planck scale measurements suggest that space and time might not be infinitely divisible, but have a quantum granularity that becomes apparent only at the smallest scales. The concept of quantum reference frames adds another layer of complexity to measurement paradoxes. In quantum mechanics, all measurements must be made relative to some reference frame, but the reference frame itself can be in a quantum state. This leads to situations where the very concept of measurement becomes ambiguous depending on which quantum reference frame is chosen. Recent developments in quantum clock synchronization highlight new paradoxes in time measurement. Quantum mechanics allows for more precise clock synchronization than classical physics, but the process of synchronizing clocks creates quantum correlations that affect their subsequent behavior. This suggests that time itself might have quantum properties that become apparent in high-precision measurements. Quantum phase transitions represent a profound paradox in physics, occurring at absolute zero temperature, where classical thermal fluctuations cease to exist. Unlike classical phase transitions driven by temperature changes, quantum phase transitions are driven by quantum fluctuations and occur when the ground state of a system fundamentally changes its character. This creates situations where quantum effects manifest at macroscopic scales, challenging our understanding of the boundary between quantum and classical behavior. The concept of quantum criticality emerges at these transition points, where quantum fluctuations become scale invariant and the system exhibits remarkable universal properties. At these critical points, the distinction between microscopic and macroscopic physics blurs, and quantum correlations can extend across all length scales. This emergence of long-range quantum coherence in systems that should be dominated by classical behavior presents a fundamental paradox in our understanding of phase transitions. Strange metal phases in high-temperature superconductors exemplify these paradoxes. In these materials, electrical resistance scales linearly with temperature, defying the standard theory of metals. This behavior suggests that these systems exist in a state of permanent quantum criticality, where quantum fluctuations dominate at temperatures far above where quantum effects should matter. Understanding how quantum critical behavior can persist at such high temperatures remains one of physics' great unsolved puzzles. The entanglement entropy of quantum critical systems reveals additional paradoxes. At critical points, the entanglement between different parts of the system follows universal scaling laws that mirror the behavior of black hole entropy. This surprising connection between quantum criticality and gravity suggests deep relationships between quantum information, phase transitions, and space-time geometry that we're only beginning to understand. Quantum phase transitions in time crystals present particularly fascinating paradoxes. These systems spontaneously break time translation symmetry, exhibiting periodic behavior in their ground state. This seems to violate fundamental principles about ground state behavior and energy conservation. Though careful analysis shows these systems remain consistent with quantum mechanics while expanding our understanding of possible phases of matter. The concept of deconfined quantum criticality challenges our traditional understanding of phase transitions. In these systems, particles that are normally confined, like quarks in nuclear physics, become free at the critical point. This liberation of quantum degrees of freedom at critical points suggests that our classification of phases of matter might be incomplete, and that new types of quantum order remain to be discovered. Many body localization near quantum critical points presents another paradox. While classical systems tend to reach thermal equilibrium, quantum systems can become stuck in non-equilibrium states due to strong disorder. This quantum phenomenon prevents the system from exploring all possible states, violating the ergodic principle that underlies much of statistical mechanics. Quantum phase transitions in topological systems add another layer of complexity. These transitions can occur between states that cannot be distinguished by any local measurement, but differ in their global topological properties. This non-local nature of topological phase transitions challenges our understanding of how quantum systems change from one state to another. The role of measurement in quantum phase transitions creates additional paradoxes. The act of measuring a system near a quantum critical point can fundamentally alter its behavior, leading to what's known as the quantum Zeno effect. This raises questions about how we can study quantum critical phenomena without disturbing the very effects we're trying to observe. Recent experiments with ultra-cold atoms have revealed new aspects of quantum criticality. These systems can be precisely controlled to explore quantum phase transitions, but they also show unexpected behaviors like quantum revival, where systems seemingly return to their initial states after passing through a critical point. This apparent violation of the second law of thermodynamics is reconciled through careful consideration of quantum coherence and entanglement. The emergence of effective field theories at quantum critical points presents another conceptual challenge. While the microscopic details of different systems may vary greatly, they can exhibit identical critical behavior described by the same effective theory. This universality suggests that quantum criticality might reveal fundamental principles about how complex quantum systems organize themselves independently of microscopic details. The quantum nature of sound presents a fascinating set of paradoxes that challenge our understanding of both quantum mechanics and acoustic phenomena. Phonons, the quantum particles of sound, exist as collective excitations of atomic vibrations, yet they behave in ways that seem to contradict our classical understanding of sound waves. These quantum acoustic effects reveal new layers of complexity in how matter and energy interact at the microscopic level. The very concept of a phonon embodies a fundamental paradox. How can a collective vibration of countless atoms behave as a single particle? Unlike photons or electrons, phonons don't exist as fundamental particles, but emerge from the quantum behavior of many particles acting together. This emergence of particle-like behavior from collective oscillations challenges our understanding of what constitutes a real particle versus an effective description of collective behavior. Quantum acoustodynamics reveals surprising parallels with quantum electrodynamics, suggesting deep connections between sound and light at the quantum level. Just as photons mediate electromagnetic forces, phonons can mediate interactions between electrons in solids, leading to phenomena like superconductivity. This quantum acoustic coupling creates situations where sound waves can influence electronic properties in ways that seem to defy classical physics. The concept of acoustic quantum dots introduces another layer of paradox. These structures can trap phonons in specific locations, creating quantum wells for sound waves. The confined phonons exhibit discrete energy levels, much like electrons in atoms, but with the peculiar feature that the particle being confined is itself a collective excitation. This nesting of quantum phenomena, quantized states of already quantum mechanical collective modes, pushes our understanding of quantum mechanics in new directions. Phonon lasers represent another quantum acoustic paradox. Similar to optical lasers but operating with sound waves, these devices create coherent acoustic beams through quantum amplification. However, unlike photons, phonons strongly interact with their environment and with each other, leading to unique quantum effects that have no direct analog in optical systems. These interactions create new possibilities for quantum control, but also raise questions about the nature of coherence in strongly interacting quantum systems. The quantum limit of sound propagation presents particularly intriguing paradoxes. At extremely low temperatures and small scales, sound waves begin to exhibit quantum tunneling and interference effects. This quantum behavior of what we typically consider a classical wave phenomenon raises fundamental questions about the boundary between quantum and classical physics in acoustic systems. Recent experiments in quantum acoustics have demonstrated the entanglement of phonons, creating situations where sound waves in different locations become quantum mechanically correlated. This phonon entanglement challenges our classical intuition about sound as a local disturbance in a medium, suggesting that acoustic phenomena can exhibit the same spooky action at a distance that Einstein found so troubling in quantum mechanics. The interaction between phonons and other quantum particles creates additional paradoxes. In some materials, phonons can couple so strongly with electrons that they form new quasi-particles called polarons. These hybrid particles blur the distinction between sound waves and matter waves, creating states that are neither purely acoustic nor purely electronic in nature. Quantum acoustic metamaterials push these paradoxes even further. These engineered structures can manipulate sound waves in ways that seem to violate classical acoustic principles, creating situations where sound travels backward, stops completely, or follows paths that should be forbidden by classical wave mechanics. The quantum behavior of phonons in these materials reveals new possibilities for controlling sound at the quantum level. The role of phonons in quantum computation presents another fascinating paradox. While phonons are typically viewed as a source of decoherence that destroys quantum information, recent research suggests they can be harnessed for quantum information processing. This dual nature of phonons as both a threat to and a resource for quantum computation challenges our understanding of the relationship between quantum information and its physical carriers. The thermodynamics of quantum acoustic systems raises additional questions about the nature of heat and sound at the quantum level. The traditional view of heat as random atomic motion becomes complicated when phonons exhibit quantum coherence and entanglement. These quantum effects suggest that thermal and acoustic phenomena might be more deeply connected than previously thought, with implications for both fundamental physics and practical applications in quantum technologies. The interaction between light and matter at the quantum level reveals some of the most striking paradoxes in modern physics. Quantum optics challenges our classical understanding of both light and matter, presenting situations where the fundamental nature of both becomes increasingly ambiguous. These light-matter interactions demonstrate quantum effects that seem to defy our everyday experience of how light and matter should behave. The concept of dressed states represents one of the most profound paradoxes in quantum optics. When atoms interact strongly with light, they form hybrid states that are neither purely atomic nor purely photonic. These dressed states exhibit properties of both matter and light simultaneously, challenging our ability to distinguish between the two. The very notion of separate light and matter entities begins to break down in these strongly coupled systems. Quantum optical phenomena, like electromagnetically induced transparency, EIT, present particularly puzzling paradoxes. In EIT, a medium that should strongly absorb light becomes completely transparent due to quantum interference effects. This seemingly impossible behavior arises from the coherent interaction between light and matter, creating quantum pathways that cancel out absorption. The fact that adding more light to a system can make it more transparent contradicts our classical intuitions about light-matter interactions. The quantum Rabi model reveals another layer of paradox in light-matter coupling. At very strong coupling strengths, The rotating wave approximation that underlies much of quantum optics breaks down, leading to counter-rotating terms that violate energy conservation on very short timescales. These violations are allowed by the uncertainty principle, but challenge our understanding of energy conservation in quantum systems. Single photon nonlinearities create situations where individual light particles can dramatically alter the properties of matter. These effects demonstrate that even a single quantum of light can induce significant changes in material systems, contrary to our classical expectation that light effects should scale smoothly with intensity. The discrete nature of these interactions reveals the fundamentally quantum character of light-matter coupling, the phenomenon of superradiance, where multiple atoms emit light collectively, presents another quantum optical paradox. The atoms behave as a single quantum entity, emitting light much more intensely than they would individually. This collective quantum behavior challenges our understanding of atomic independence and suggests that quantum correlations can dramatically enhance light-matter interactions. Quantum memories based on light-matter interfaces reveal paradoxes about the nature of quantum information storage. These systems can transfer quantum states between light and matter, preserving quantum information while changing its physical form entirely. The ability to coherently convert between such different physical manifestations of quantum information raises questions about the fundamental nature of quantum states. The development of photonic molecules and quantum optical circuits introduces new paradoxes about the nature of synthetic quantum systems. These engineered structures can trap and manipulate light in ways that mirror the behavior of atomic systems, creating artificial atoms and molecules made purely of light. The emergence of matter-like behavior in purely photonic systems challenges our understanding of the distinction between light and matter. Recent experiments with quantum polaritons, hybrid light-matter particles, demonstrate situations where the properties of light and matter become so thoroughly mixed that neither description alone suffices. These quasi-particles can form quantum condensates that exhibit both the coherence properties of light and the interaction properties of matter, creating new states of matter that transcend traditional classifications. The quantum Zeno effect in optical systems presents another fascinating paradox. Continuous observation of a quantum optical system can freeze its evolution, preventing transitions that would otherwise occur. This effect demonstrates how measurement can dramatically alter the dynamics of light-matter interactions, raising questions about the nature of observation in quantum systems. The creation of quantum optical bound states, where photons effectively attract each other through their interaction with matter, challenges our understanding of photon interactions. While photons normally pass through each other without interaction, these bound states demonstrate that light can be made to interact with itself through the mediation of matter, creating new possibilities for quantum information processing and quantum simulation. Topological quantum phenomena represent some of the most enigmatic paradoxes in physics, where the global properties of quantum systems become more important than their local details. These effects challenge our understanding of quantum mechanics by introducing states of matter that can't be characterized by traditional symmetry breaking, but instead are defined by mathematical properties that remain invariant under continuous deformations. The quantum Hall effect exemplifies these topological paradoxes. When electrons are confined to two dimensions in strong magnetic fields, they form states characterized by precisely quantized conductance values that depend only on fundamental constants. This quantization is incredibly robust, maintaining its exact value regardless of sample impurities or geometric details. The paradox lies in how such precise universal behavior can emerge from complex, disordered systems. Topological insulators present another fascinating paradox. Materials that are electrical insulators in their bulk, but conduct electricity perfectly on their surfaces. These surface states are protected by topology, making them immune to certain types of disorder. The existence of these robust conducting states challenges our traditional understanding of electrical conductivity and band theory, suggesting deeper principles about how quantum states organize themselves. The concept of anyones, particles that are neither bosons nor fermions, emerges from topological quantum states. These particles can acquire arbitrary quantum statistics when confined to two dimensions, defying our usual classification of all particles as either bosons or fermions. Even more remarkably, some anyones retain a memory of their past movements through space, encoding information in their braiding patterns. Majorana zero modes represent particularly puzzling topological entities. These quantum states are their own antiparticles and can appear at the ends of certain quantum wires or in vortices of topological superconductors. The paradox lies in how these states can be both particle and antiparticle simultaneously, and how they can maintain quantum coherence despite being spatially separated. The concept of topological order introduces new types of quantum entanglement that can't be destroyed by local perturbations. This long-range entanglement creates states of matter that can't be described by local order parameters, challenging our traditional framework for understanding phases of matter. The stability of these topological states seems to violate our expectations about how quantum systems should respond to disturbances. Quantum spin liquids present another topological paradox. These states avoid magnetic ordering even at absolute zero temperature, maintaining a quantum superposition of different spin configurations. The emergence of fractional excitations in these systems, where electrons appear to split into more fundamental particles, challenges our understanding of particle indivisibility and the nature of quantum numbers. The relationship between topology and quantum computation reveals additional paradoxes. Topological quantum computers would store and process information in the braiding patterns of anyones, making the computation immune to local disturbances. This suggests that some quantum information might be fundamentally more robust when encoded in topological degrees of freedom rather than local quantum states. Recent experiments with synthetic quantum matter have created new types of topological states that don't exist in natural materials. These engineered systems can exhibit properties like fractional charges and magnetic monopoles, raising questions about what quantum properties are truly fundamental and what can emerge from careful manipulation of quantum systems. The connection between topology and symmetry in quantum systems presents another layer of paradox. Symmetry-protected topological phases demonstrate that certain quantum properties can be protected by symmetries even when the system's topology appears trivial. This interplay between symmetry and topology suggests deeper principles about how quantum systems organize themselves to protect certain properties. The study of topological quantum field theories reveals surprising connections between quantum mechanics and mathematics. These theories describe physical systems whose properties depend only on global topological features, suggesting that some aspects of quantum mechanics might be more fundamentally related to mathematics than to traditional physical concepts like force or energy. Quantum magnetism reveals some of the most intriguing paradoxes in condensed matter physics, where the interplay between quantum mechanics and magnetic interactions leads to phenomena that defy classical intuition. The behavior of quantum spin systems challenges our fundamental understanding of order, symmetry, and the collective behavior of quantum particles. The quantum nature of spin itself presents an immediate paradox. Unlike classical magnetic moments that can point in any direction, quantum spins exist in superpositions of states that collapse to specific values only when measured. This quantization of spin directions has no classical analog and leads to phenomena like quantum tunneling of magnetization, where the magnetic moment of a system can flip without passing through intermediate orientations. Geometric frustration in quantum magnets creates particularly fascinating paradoxes. When spins are arranged in certain geometric patterns, like triangular or Kagome lattices, they cannot satisfy all their interaction preferences simultaneously. This frustration can prevent the system from settling into a classical ordered state, instead maintaining quantum fluctuations even at absolute zero temperature. The resulting quantum spin-liquid states challenge our understanding of how matter organizes itself at low temperatures. The Kondo effect demonstrates another quantum magnetic paradox, where a single magnetic impurity in a metal can dramatically alter the material's electronic properties. As temperature decreases, the impurity's magnetic moment becomes increasingly screened by conduction electrons, forming a complex many-body state that cannot be described by single particle physics. This screening process reveals the intricate interplay between quantum magnetism and electronic behavior. Quantum spin chains exhibit peculiar entanglement properties that seem to violate our expectations about locality. Even in systems with only nearest neighbor interactions, quantum correlations can extend across long distances, creating patterns of entanglement that encode sophisticated quantum information. These long-range correlations challenge our understanding of how quantum effects propagate through materials. The emergence of fractional excitations in quantum magnets presents another layer of paradox. In certain magnetic systems, exciting the material doesn't create simple spin waves, but instead produces particles carrying fractional quantum numbers. These fractional excitations, like spinons, cannot exist as individual particles, but must always be created in pairs, demonstrating how collective quantum behavior can give rise to seemingly impossible particle properties. Quantum criticality in magnetic systems reveals situations where quantum fluctuations dominate even at relatively high temperatures. Near certain quantum phase transitions, magnetic materials can exhibit strange metal behavior where traditional quasi-particle descriptions break down. This persistence of quantum effects at elevated temperatures challenges our understanding of the quantum to classical transition. The interplay between quantum magnetism and topology creates additional paradoxes. Certain magnetic materials can host topologically protected spin textures, like skyrmions, that behave as particles despite being collective excitations of many spins. These topological spin structures demonstrate how quantum magnetic systems can create emergent particles with properties unlike anything found in isolated quantum systems. Recent experiments with artificial quantum magnets created using ultra-cold atoms or superconducting circuits have revealed new aspects of quantum magnetism. These synthetic systems can realize magnetic interactions that don't exist in natural materials, creating novel quantum states that challenge our understanding of what kinds of magnetic order are possible. The relationship between quantum magnetism and quantum computation presents intriguing possibilities and paradoxes. Magnetic quantum systems might be used to perform quantum computations, encoding information in spin states and manipulating it through magnetic interactions. However, the very quantum fluctuations that make these systems interesting also make them difficult to control, creating a fundamental tension between quantum coherence and computational utility. The concept of order by disorder in quantum magnets reveals another fascinating paradox. In some cases, quantum fluctuations can actually help establish magnetic order in systems that would remain disordered classically. This phenomenon, where disorder leads to order through quantum effects, challenges our classical intuition about the relationship between fluctuations and ordering. Quantum turbulence represents one of the most enigmatic phenomena in physics, where quantum effects manifest in fluid dynamics at macroscopic scales. Unlike classical turbulence, which involves continuous fluid flow, quantum turbulence occurs in superfluids and consists of a tangle of discrete, quantized vortices. This quantization of fluid motion presents fundamental paradoxes about the nature of flow and vorticity in quantum systems. The very existence of superfluidity challenges our classical understanding of fluid dynamics. At low temperatures, certain fluids can flow without any viscosity, seemingly violating the principles of classical fluid mechanics. This quantum coherent flow state emerges from the collective behavior of countless particles, acting in perfect quantum synchronization, creating a macroscopic quantum state that extends throughout the fluid. Quantum vortices and superfluids present particularly fascinating paradoxes. Unlike classical vortices, which can have any strength, quantum vortices are quantized. Their circulation can only occur in discrete units determined by fundamental constants. This quantization creates situations where fluid rotation can only change through discrete jumps, contradicting our classical expectation of smooth, continuous changes in fluid motion. The interaction between quantum vortices reveals another layer of paradox. When quantum vortices approach each other, they don't merge like classical vortices, but instead can become quantum mechanically entangled. This entanglement can lead to the formation of vortex knots and links that maintain their topology due to quantum effects, creating stable structures that have no classical analog. The phenomenon of quantum turbulence cascade presents a unique paradox in fluid dynamics. While classical turbulence involves a continuous cascade of energy from large to small scales, quantum turbulence involves both a classical-like cascade at large scales and a quantum cascade at small scales where individual vortices interact. This dual nature of the energy cascade challenges our understanding of how energy flows through fluid systems. Recent experiments with quantum turbulence in Bose-Einstein condensates have revealed surprising connections to cosmic phenomena. The formation and evolution of quantum vortex tangles show similarities to the cosmic web of matter in the universe, suggesting deep connections between quantum fluid dynamics and cosmological structure formation. This unexpected parallel raises questions about the universality of turbulent behavior across vastly different scales. The relationship between quantum turbulence and quantum information presents another fascinating paradox. The complex network of entangled vortices in quantum turbulence can encode and process quantum information in ways that classical turbulence cannot. This suggests that turbulent quantum fluids might serve as novel platforms for quantum computation, though controlling and manipulating this information remains a significant challenge. The emergence of quantum turbulence in rotating superfluids creates situations where the fluid forms a regular lattice of quantized vortices before transitioning to turbulent behavior. This ordered to chaotic transition challenges our understanding of how quantum systems maintain or lose coherence, and how classical chaos emerges from quantum dynamics. The interaction between sound waves and quantum turbulence reveals additional paradoxes. Unlike classical turbulence, where sound waves are scattered randomly, quantum turbulence can interact with sound in highly coherent ways, creating quantum acoustic effects that have no classical counterpart. This quantum classical hybrid behavior suggests new ways of probing and controlling turbulent quantum systems. The role of quantum turbulence in neutron stars presents particularly intriguing possibilities. The superfluid interior of neutron stars may host complex networks of quantized vortices, influencing the star's rotation and potentially explaining observed phenomena like pulsar glitches. This connection between quantum fluid dynamics and astrophysics demonstrates how quantum effects can influence even the largest structures in the universe. The study of quantum turbulence has also revealed surprising connections to quantum chaos theory. While classical chaos involves continuous trajectories becoming unpredictable, quantum turbulence involves discrete vortices whose dynamics are fundamentally probabilistic. This quantum unpredictability creates new challenges for understanding and predicting turbulent behavior in quantum fluids. Quantum transport phenomena reveal some of the most counterintuitive aspects of electron behavior in materials, where the wave nature of particles leads to effects that defy classical expectations. The movement of electrons through materials at the quantum level presents paradoxes that challenge our fundamental understanding of electrical conductivity and resistance. The quantum Hall effect stands as a prime example of these transport paradoxes. In strong magnetic fields, the Hall conductance becomes exactly quantized in integer or fractional multiples of fundamental constants, regardless of material impurities or geometric details. This precise quantization emerges from the complex quantum choreography of electrons, demonstrating how quantum effects can produce exactitude from apparent chaos. Ballistic electron transport creates situations where electrons can flow through materials without any resistance. Unlike classical conductors, where electrons scatter off impurities and lose energy, quantum ballistic transport allows electrons to maintain quantum coherence over macroscopic distances. This seemingly impossible perfect conductivity challenges our classical understanding of electrical resistance. The phenomenon of Klein tunneling presents another transport paradox, where relativistic quantum particles can penetrate potential barriers with perfect transmission, regardless of the barrier's height. This effect, first predicted for high-energy particles, has been observed in materials like graphene, where electrons behave as massless Dirac fermions. The ability of particles to freely penetrate seemingly impenetrable barriers contradicts classical intuition about particle motion. Quantum interference effects in electronic transport lead to fascinating phenomena like weak localization and anti-localization. These effects arise from the quantum interference of electron waves traveling along different paths, causing either enhanced or reduced resistance depending on the strength of spin-orbit coupling. The fact that quantum interference can both increase and decrease conductivity represents a paradox in our understanding of electron transport. The emergence of topological protection in quantum transport creates channels where electrons can flow without backscattering, even in the presence of disorder. These topologically protected states arise from the global properties of electronic wave functions rather than local material properties, challenging our understanding of how robust transport can emerge in imperfect systems. Quantum pumping represents another transport paradox, where periodic variations of system parameters can create directed electron flow without applying a voltage difference. This quantum mechanical pump effect demonstrates how geometric phases in quantum evolution can lead to particle transport, revealing deep connections between quantum geometry and electron motion. The interaction between electron transport and quantum measurement presents additional paradoxes. The act of measuring current flow can affect the quantum state of the electrons, leading to phenomena like the quantum Zeno effect in transport. This interplay between measurement and quantum coherence raises fundamental questions about how we observe and characterize quantum transport. Recent experiments with artificial quantum matter have revealed new aspects of quantum transport. Using synthetic quantum systems, researchers can create and control transport phenomena that don't exist in natural materials, expanding our understanding of what kinds of quantum motion are possible. These engineered systems demonstrate how quantum transport can be manipulated in ways that seem to violate classical transport theory. The relationship between quantum transport and thermodynamics creates additional paradoxes. Quantum heat engines based on electron transport can achieve efficiencies beyond classical limits by exploiting quantum coherence and entanglement. These quantum thermodynamic devices challenge our understanding of the relationship between work, heat, and quantum information. The concept of many-body localization in quantum transport systems reveals situations where quantum effects prevent thermalization, leading to persistent, non-equilibrium states. This violation of ergodicity challenges our fundamental assumptions about how quantum systems approach equilibrium and how transport properties emerge in interacting systems. The intersection of quantum mechanics and chemical bonding reveals profound paradoxes that challenge our understanding of how atoms combine to form molecules. Quantum chemistry presents situations where the very nature of chemical bonds defies classical intuition, creating phenomena that can only be explained through the lens of quantum mechanics. The quantum nature of the chemical bond itself presents an immediate paradox. Unlike classical models of fixed electron pairs between atoms, quantum mechanical bonds exist as superpositions of different electronic configurations. This quantum superposition means that electrons and chemical bonds aren't simply shared between atoms, but exist in complex quantum states that spread across entire molecular structures. Quantum tunneling in chemical reactions creates particularly fascinating paradoxes. Reactions that should be impossible, according to classical chemistry, can proceed through quantum tunneling, where reactants bypass energy barriers rather than crossing over them. This quantum shortcut through reaction barriers challenges our classical understanding of chemical kinetics and thermodynamics. The concept of resonance in quantum chemistry presents another layer of paradox. Molecules like benzene can't be adequately described by any single structural formula, but exist as quantum superpositions of multiple structures simultaneously. This quantum resonance isn't just a mathematical convenience, but reflects the true nature of molecular bonding, where electron distributions fluctuate between different configurations. Zero-point energy in molecular systems reveals how quantum effects prevent molecules from ever being truly static, even at absolute zero temperature. Atoms in molecules continue to vibrate due to quantum uncertainty, creating a fundamental limit to molecular stability. This perpetual quantum motion challenges our classical picture of molecules as rigid structures with fixed atomic positions. The phenomenon of quantum entanglement in chemical bonds reveals surprising connections between separated parts of molecules. Electrons in chemical bonds can become entangled in ways that affect molecular properties and reactivity, creating non-local quantum correlations that influence chemical behavior. This quantum non-locality in molecular systems challenges our understanding of how chemical properties emerge from electronic structure. Recent developments in quantum biology have revealed how quantum coherence can persist in biological molecules despite warm, wet conditions. The ability of biological systems to maintain quantum effects that typically require carefully controlled laboratory conditions presents a paradox about the role of quantum mechanics in life processes. The study of molecular quantum computers reveals how chemical systems can process quantum information through their electronic and nuclear spin states. These molecular quantum systems demonstrate that quantum computation isn't limited to artificial devices, but can occur naturally in chemical systems, raising questions about the relationship between quantum information and chemical processes. Quantum interference in molecular electronics creates situations where electrical conductance through molecules depends on quantum phase relationships rather than classical electron flow. This quantum behavior leads to effects like destructive interference in molecular conductance, where adding additional conduction pathways can actually decrease overall conductivity. The role of quantum nuclear effects in chemical reactions presents additional paradoxes. The quantum nature of atomic nuclei can significantly affect reaction rates and pathways, particularly for light atoms like hydrogen. These nuclear quantum effects demonstrate that even the classical parts of molecules must sometimes be treated quantum mechanically. The emergence of collective quantum behavior in molecular crystals reveals how quantum effects can scale up from individual molecules to macroscopic systems. Phenomena like superradiance and polariton formation in molecular aggregates demonstrate quantum coherence extending across many molecules, challenging our understanding of the quantum to classical transition. The realm of quantum simulation and computation presents some of the most perplexing paradoxes in modern physics, where the very act of computing becomes entangled with fundamental quantum phenomena. These paradoxes challenge our understanding of both computation and quantum mechanics, revealing deep connections between information processing and physical reality. The quantum speed-up paradox stands at the heart of quantum computation. Quantum computers can solve certain problems exponentially faster than classical computers, apparently performing more computational steps than the number of physical operations executed. This quantum parallelism, where multiple computations seem to occur simultaneously in superposition, challenges our classical understanding of how computation relates to physical processes. The relationship between quantum entanglement and computational power presents another fascinating paradox. While entanglement is often viewed as a resource that enables quantum computational advantage, too much entanglement can actually make quantum states impossible to simulate efficiently. This suggests a sweet spot in quantum complexity where computational power is maximized, challenging our intuition about the relationship between quantum resources and computational capability. Quantum error correction reveals particularly striking paradoxes. Classical information can be protected against errors by simple redundancy, but quantum information cannot be perfectly copied due to the no-cloning theorem. Yet quantum error correction schemes can protect quantum information by encoding it in entangled states spread across multiple qubits. This ability to protect information that cannot be copied presents a fundamental paradox in quantum information theory. The concept of quantum supremacy introduces new paradoxes about the nature of computation itself. When a quantum computer performs a calculation that no classical computer could practically achieve, how do we verify the result? This verification paradox highlights deep questions about the relationship between quantum and classical computation, and what it means to solve a problem quantum mechanically. Quantum simulation of physical systems presents another layer of paradox. While classical computers struggle to simulate quantum systems due to the exponential growth of the quantum state space, quantum simulators can efficiently mimic other quantum systems. This raises questions about the relationship between physical reality and computation. Is the universe itself performing some kind of quantum computation? The role of measurement in quantum computation creates additional paradoxes. While quantum algorithms often rely on maintaining quantum coherence throughout the computation, the final result must be extracted through measurement, which collapses the quantum state. This tension between the need for both quantum coherence and classical measurement challenges our understanding of how quantum information can be usefully processed. Recent developments in quantum machine learning reveal new paradoxes about the relationship between quantum mechanics and artificial intelligence. Quantum neural networks can process information in ways that have no classical analog, suggesting forms of machine learning that operate according to fundamentally quantum principles. This raises questions about the nature of learning and intelligence in quantum systems. The concept of quantum computational complexity introduces paradoxes about the limits of computation in our universe. Some quantum states, while physically possible, may be computationally complex to create or verify. This suggests fundamental limits on what kinds of quantum states can be practically realized, even if they're allowed by the laws of physics. The relationship between quantum computation and thermodynamics presents fascinating paradoxes. Quantum computers must maintain coherence to operate, yet the act of computation inevitably generates heat and entropy. This creates a fundamental tension between the need for quantum isolation and the unavoidable thermodynamic costs of information processing. The emergence of topological quantum computation suggests new ways of thinking about information processing in quantum systems. By encoding information in topological properties of quantum states, these systems could potentially perform computations that are inherently protected against errors. This connection between topology and computation reveals deep relationships between mathematical structure and physical information processing. The intersection of quantum measurement and control theory reveals some of the deepest paradoxes in quantum mechanics, where the act of observing and manipulating quantum systems challenges our fundamental understanding of causality and interaction. These paradoxes emerge from the inherent tension between our desire to control quantum systems and the quantum principles that seem to resist such control. The quantum control paradox emerges from the fundamental conflict between quantum coherence and measurement. To control a quantum system, we need to measure its state, but measurement inevitably disturbs the very quantum properties we're trying to control. This creates a delicate balance between gaining information about a system and maintaining its quantum properties, challenging our classical notions of observation and control. Quantum feedback control presents particularly fascinating paradoxes. Unlike classical feedback systems, where measurements can be made continuously without disturbing the system, quantum feedback must contend with the fact that each measurement fundamentally alters the system's state. This creates situations where the act of monitoring a quantum system can either preserve or destroy quantum properties, depending on how the measurement is performed. The concept of weak measurement introduces another layer of paradox in quantum control. These measurements, which barely disturb the quantum system, can sometimes yield measurement results that lie outside the expected range of values for the measured property. These anomalous weak values challenge our understanding of what measurement means in quantum mechanics and how it relates to the underlying reality of quantum systems. Quantum state preparation reveals paradoxes about the relationship between control and initialization. While classical systems can be prepared in well-defined initial states, quantum systems resist such precise preparation due to the uncertainty principle. Yet quantum control protocols must somehow navigate this fundamental uncertainty to create desired quantum states, leading to sophisticated control strategies that work with, rather than against, quantum uncertainty. The emergence of quantum error correction in control theory presents additional paradoxes. While it's impossible to perfectly copy or measure quantum information, error correction schemes can protect quantum states by spreading information across multiple quantum systems. This apparent circumvention of the no-cloning theorem through clever control protocols reveals deep connections between measurement, control, and quantum information. Recent developments in quantum reservoir engineering show how controlled interaction with an environment can actually preserve quantum properties rather than destroy them. This counterintuitive effect, where coupling to an environment enhances rather than degrades quantum coherence, challenges our understanding of the relationship between quantum systems and their surroundings. The role of measurement back action in quantum control creates situations where the act of measurement can be harnessed as a control tool. Rather than viewing measurement disturbance as a nuisance to be minimized, quantum control protocols can use measurement back action to steer quantum systems toward desired states. This reimagining of measurement as a control resource represents a fundamental shift in how we think about quantum measurement. Quantum optimal control theory reveals paradoxes about the limits of controllability in quantum systems. While quantum mechanics allows for arbitrary unitary transformations between states, practical constraints on control fields and measurement capabilities create fundamental limits on what states can be achieved. These limitations arise not from quantum mechanics itself, but from the interplay between quantum dynamics and control resources. The concept of measurement-based quantum control presents new paradigms for manipulating quantum systems. Instead of directly applying control fields, these protocols use carefully designed measurements to induce desired quantum evolution. This indirect control through measurement challenges our classical intuition about how physical systems can be manipulated. The relationship between quantum control and thermodynamics reveals additional paradoxes. Control operations inevitably require energy and generate entropy. Yet, quantum systems must maintain coherence to remain useful. This creates fundamental trade-offs between control precision and thermodynamic cost, suggesting deep connections between information, control, and energy in quantum systems. The concept of emergence in quantum systems presents us with the ultimate paradoxes in physics, where collective quantum phenomena give rise to new principles and behaviors that transcend their microscopic origins. These emergent phenomena challenge our reductionist assumptions about how complex systems arise from simple components, revealing deeper truths about the nature of reality itself. The emergence of classicality from quantum mechanics represents perhaps the most fundamental paradox in physics. How does our familiar classical world, with its apparent objectivity and locality, emerge from the strange quantum realm of superpositions and entanglement? This quantum to classical transition suggests that reality itself might be layered, with different physical principles becoming relevant at different scales. Universal behavior in quantum systems presents another profound paradox. Despite the vast complexity of quantum systems, they often display remarkably simple, universal properties that depend only on a few basic parameters. This emergence of simplicity from quantum complexity challenges our understanding of how physical laws scale, from microscopic to macroscopic levels. The holographic principle reveals perhaps the deepest emergent paradox: the possibility that our three-dimensional reality emerges from information encoded on a two-dimensional boundary. This suggests that dimensionality itself might be an emergent property, rather than a fundamental aspect of reality, raising questions about the true nature of space, time, and information. Quantum criticality demonstrates how systems poised between different phases of matter can exhibit universal behavior independent of microscopic details. At these critical points, quantum fluctuations at all scales become important, creating situations where the distinction between microscopic and macroscopic physics breaks down. This scale invariance suggests fundamental principles about how nature organizes itself at quantum transitions. The emergence of space and time from quantum mechanics presents particularly fascinating paradoxes. Various approaches to quantum gravity suggest that space-time itself might not be fundamental, but emerges from more basic quantum mechanical principles. This would mean that our most basic concepts of reality, space, and time themselves are emergent phenomena rather than fundamental ingredients of the universe. Recent developments in quantum many-body physics reveal how collective quantum behavior can give rise to entirely new types of particles and excitations. These emergent particles, like anyons and magnetic monopoles, have properties that cannot exist for fundamental particles, demonstrating how quantum systems can create new possibilities beyond those available to their constituent parts. The concept of quantum Darwinism suggests that the classical reality we observe emerges through a kind of natural selection process acting on quantum states. Only those quantum states, robust enough to create multiple records in the environment, become part of our classical reality. This environmental selection process provides a new perspective on how objective classical properties emerge from the quantum realm. The relationship between emergence and quantum information reveals additional paradoxes. While quantum systems contain exponentially more information than classical systems of the same size, most of this information remains hidden in quantum correlations. Only a tiny fraction becomes accessible as classical information, raising questions about the nature of information and its role in physical reality. Looking back across all our explorations of quantum paradoxes, from the basic principles of quantum mechanics to the most advanced frontiers of modern physics, we see a common thread: the fundamental role of emergence in shaping our understanding of reality. Each paradox we've encountered reveals another layer of emergence, another way in which simple quantum principles give rise to complex and often surprising phenomena. As we conclude our journey through physics' greatest paradoxes, we're left with a profound appreciation for the mysterious nature of reality. These paradoxes aren't merely puzzles to be solved, but windows into the fundamental structure of the universe. They remind us that nature operates according to principles that often transcend our classical intuitions, revealing a reality far richer and more fascinating than we could have imagined. The intersection of quantum mechanics and machine learning reveals entirely new classes of paradoxes that challenge our understanding of both quantum physics and artificial intelligence. As we venture into this frontier where quantum systems meet computational learning, we encounter phenomena that push the boundaries of what we consider possible in both fields. The quantum advantage paradox in machine learning presents a fascinating conundrum. While quantum computers can process certain types of information exponentially faster than classical computers, the act of reading out the results of quantum machine learning algorithms often negates this advantage. This creates a fundamental tension between quantum processing power and our ability to access its results meaningfully. Quantum neural networks introduce new paradoxes about the nature of learning in quantum systems. Unlike classical neural networks, where information flows through well-defined pathways, quantum neural networks can exist in superpositions of different network configurations simultaneously. This quantum parallelism in learning architectures raises profound questions about how information processing and learning occur in quantum systems. The concept of quantum feature spaces presents another layer of paradox. While classical machine learning algorithms work in finite dimensional feature spaces, quantum systems can exploit infinite dimensional Hilbert spaces for data representation. This quantum advantage in representation power seems to violate our intuitive understanding of how information can be processed and stored. Quantum reinforcement learning reveals particularly striking paradoxes about decision-making in quantum systems. When quantum agents interact with quantum environments, the very notion of state and action becomes blurred by quantum uncertainty and entanglement. This creates situations where the learning process itself exists in a quantum superposition, challenging our classical understanding of how systems learn from experience. The emergence of quantum generative models presents new paradoxes about the relationship between quantum systems and probability. These models can generate quantum states that exhibit correlations impossible in classical systems, suggesting that quantum probability distributions might be fundamentally different from their classical counterparts. This raises questions about the nature of randomness and generation in quantum systems. Recent developments in quantum kernel methods reveal how quantum systems can recognize patterns that have no classical analog. These quantum patterns emerge from interference effects in high-dimensional Hilbert spaces, creating classification boundaries that cannot be realized by classical algorithms. This suggests that quantum systems might perceive and categorize information in fundamentally different ways than classical systems. The role of measurement in quantum machine learning creates additional paradoxes. While classical machine learning algorithms can observe their input data freely, quantum algorithms must contend with the fact that measurement disturbs quantum states. This creates a fundamental trade-off between gathering information about the quantum system and preserving its quantum properties for computation. Quantum federated learning introduces paradoxes about distributed quantum computation. When multiple quantum systems learn collectively while maintaining quantum coherence, the resulting distributed quantum state can exhibit correlations that seem to violate local realism. This suggests new ways of thinking about collective learning in quantum systems. The concept of quantum meta-learning raises questions about how quantum systems can learn to learn. When the learning process itself is quantum mechanical, the distinction between the learner and the learning algorithm becomes blurred by quantum effects. This creates situations where the meta-learning process exists in quantum superposition, suggesting new paradigms for adaptive quantum algorithms. The relationship between quantum learning and quantum error correction presents fascinating paradoxes. While quantum systems are inherently fragile and susceptible to decoherence, quantum learning algorithms might be able to adapt to and correct errors dynamically. This suggests a form of quantum resilience that emerges from the learning process itself, challenging our understanding of both quantum control and machine learning. The frontier of quantum metamaterials reveals new classes of paradoxes that emerge when we deliberately engineer materials to exploit quantum effects. These artificial quantum systems demonstrate properties that seem to violate our fundamental understanding of how materials should behave, creating phenomena that exist at the boundary between the natural and the engineered quantum world. The concept of quantum emulation in metamaterials presents an immediate paradox. These engineered structures can mimic quantum systems that don't exist in nature, creating artificial atoms and molecules with properties that seem impossible according to conventional quantum mechanics. Yet these systems operate entirely within the laws of quantum physics, suggesting that our understanding of what's possible in quantum systems might be too limited. Time crystals in quantum metamaterials present particularly fascinating paradoxes. These systems spontaneously break time translation symmetry, exhibiting periodic behavior in their ground state without energy input. This apparently perpetual motion in the quantum ground state challenges our understanding of both quantum mechanics and thermodynamics, suggesting new possibilities for quantum phase matter. The emergence of topological states in engineered quantum systems reveals another layer of paradox. By carefully designing the structure of quantum metamaterials, we can create protected quantum states that are immune to certain types of perturbation. These topologically protected states seem to violate our expectations about how quantum systems should respond to disturbances, revealing new principles about the relationship between geometry and quantum behavior. Quantum metamaterials that manipulate light in seemingly impossible ways create additional paradoxes. These materials can bend light backwards, slow it to a crawl, or even trap it completely, challenging our classical understanding of how electromagnetic waves should behave. The ability to engineer these effects through quantum design principles suggests deeper connections between quantum mechanics and classical wave phenomena. The concept of quantum sensing with metamaterials introduces paradoxes about measurement and detection. These engineered systems can achieve sensitivities beyond what should be possible, according to classical physics, exploiting quantum effects to measure quantities with unprecedented precision. This quantum enhancement of sensing capabilities raises questions about the fundamental limits of measurement and detection. Recent developments in quantum acoustic metamaterials reveal how we can control sound waves using quantum effects. These systems can manipulate phonons, quantum particles of sound, in ways that seem to violate classical acoustic principles. The ability to engineer quantum control over mechanical vibrations suggests new possibilities for quantum information processing and quantum sensing. The relationship between quantum metamaterials and entropy presents fascinating paradoxes. Some engineered quantum systems can appear to violate the second law of thermodynamics locally, though careful analysis shows they remain consistent with fundamental physical laws. These apparent violations reveal new aspects of how quantum systems can manipulate and control energy flow. Quantum metamaterials that exhibit negative refraction present another class of paradoxes. These materials can bend light in ways that seem to violate causality, though closer examination shows they remain consistent with special relativity. The ability to engineer such extreme optical properties challenges our understanding of how light interacts with matter at the quantum level. The emergence of collective quantum behavior in engineered systems reveals paradoxes about quantum coherence. Arrays of artificial atoms in quantum metamaterials can maintain quantum coherence over macroscopic distances, defying our expectations about how quickly quantum effects should disappear in large systems. This suggests new principles about how quantum behavior can be preserved and controlled in engineered systems. The development of quantum routers and switches in metamaterials creates paradoxes about the flow of quantum information. These devices can control the path of quantum states in ways that seem to violate the no-cloning theorem, though careful analysis shows they operate within the constraints of quantum mechanics. The ability to engineer quantum information flow reveals new possibilities for quantum networks and quantum computation. Up next, you've got two more standout theory right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out.